Next we have number 10, where there are two parts. This is part A. A positive integer capital N is given, then we have to show this identity. Summation of mu of n, mu of small n is the index of summation, times the greatest integer value of capital N divided by small n, as small n goes from 1 to capital N is equal to 1. Solution by theorems 6, 6 and 6, 11. We consider the left hand side, that becomes equal to this double summation. The outer summation is of course this summation, and the inner summation comes from this being equal to this. Summation of mu of d, where d varies over the set of positive divisors of small n, the index of the outer summation. You go and see the statements of these theorems. One of them has been used to write this one. You figure out which one. I mean, it's a simple thing. And now we are going to continue. And then in the next line, we write this outer sum in detail. I mean, without using the summation symbol, which of course gives us this sum, each term of which is this inner sum corresponding to one value of n, as small n goes from 1 to capital N. So here first you have 1, then you have 2, and like that it goes, and finally you have capital N. I have mentioned both these theorems at once because one of them has been used in this step and the other one will be now used to write what the values of these sums are. The values are just this. The first one has value 1 and the others all have value 0. And that's how we get 1, and that finally proves our identity. Note carefully that even when capital N is 1, at least this term is there. These others may not be there, and that does not affect anything. We get 1 ultimately. And next we have part B, which has this inequality. The absolute value of this sum is less than or equal to 1. Summation mu of small n divided by small n, as small n goes from 1 to capital N. Capital N is that capital N, some positive integer. We begin the solution by looking at some first few values of capital N and see if the inequality is true in those cases. So when capital N is 1, then this is our left hand side of this inequality, and this sum has only one term, mu of 1 divided by 1, which is equal to 1. So in this case we are getting equality. So that justifies the presence of this option for equality. Then when capital N is 2, then you are getting mu of 1 divided by 1, which is 1, plus mu of 2 divided by 2. Mu of 2 is minus 1. You go back and see the definition of the mu function, you will see why it's minus 1. So that way we get 1 minus 1 over 2, which is 1 divided by 2, and its absolute value is also 1 divided by 2, which is less than 1. So that means in this case we are getting inequality. And when capital N is 3, then we similarly have this. The first two of course are this, and then the next one is mu of 3 divided by 3. Mu of 3 is also minus 1, and that's why we are getting minus 1 over 3. And you calculate the value, whatever it is. Whatever it is means I think it will be 1 divided by 6, because 6 minus, yes, so that is also less than 1. And we are going to see two more values of capital N, and then we will see the general case. Well, actually we need to see only one more case separately, which corresponds to capital N equal to 4. In this case, all these things will be there, but along with them we will also have plus mu of 4 divided by 4. Mu of 4 is 0, because 4 is divisible by the square of the prime 2. It's in fact equal to 2 squared. But anyway, so we get 0 here, and again of course the same thing, this is less than 1. So that means our inequality is true for these first 4 values of capital N, and that is why we can now assume capital N to be at least 5. We need this. Okay, so that's why we had to check these other cases separately. Now next we recall something we already know about the greatest integer function. Namely that for any real number x, x equals its greatest integer value plus theta for some real number theta satisfying these inequalities. Theta is non-negative and less than 1. And to show that theta depends on x, we are, instead of writing theta, we are going to write this notation. X within curly brackets. This does not mean the singleton set x, okay. It just means that extra part that comes with the greatest integer function. Now next let's consider this quantity. Why we suddenly have to consider this, it's difficult to say. Okay, this is how we get the solution. That much I can say. So here we are looking at the absolute value of 1 plus summation of mu n times this. These curly brackets indicate this thing. Okay, so this capital N divided by small n within curly brackets means that when you express capital N divided by small n, think of capital N over small n in place of x as its greatest integer value plus that extra thing. It is that extra thing. Okay, so that's what we are considering. Because we have absolute value, we can use our ordinary triangle inequality to write that this is less than or equal to, you just apply the absolute value to each term of this sum, including that 1 of course. The absolute value of 1 is of course 1 plus summation. Inside we have pushed the absolute value. So ideally I should have written one more line, the absolute value of mu n times this. But that by one of the properties of the absolute value function equals the product of their absolute values. Now next you consider this fact that these extra parts are all less than 1 by definition because they are theta. Okay, in each case it's theta, and they are also non-negative, that means greater than or equal to 0. So their absolute values, which are in fact appearing here, are themselves, and they are less than 1 for all small n varying from 1 through capital N. And additionally also mu of 4 is equal to 0. Now you use this information here. You first write this thing. So we have this, that is less than or equal to this. Now in this sum you think of all these things. There will be the value 4 for small n to take. Why? Because capital N is greater than or equal to 5, remember. And because mu of 4 is 0, that corresponding term will vanish. Other terms will be there. Now what about the other terms? In every term, this part is less than 1. So if we use this inequality in those terms, we get the fact that this entire thing is less than or equal to 1 plus summation mod mu n. In place of this there will be nothing because we have replaced that by 1. Now what about these absolute values of mu n? You go back and see the definition of mu n. Every mu value is either 0 or minus 1 or 1. But because we have absolute value, so it's either 0 or 1. So at most each such mu value will be 1. Either it's 0 or 1. So that means if we further use this fact, then we can write that this sum is less than or equal to the sum of that many ones as many terms this sum has, taking into account that one of the terms has vanished because of this fact. Originally there were capital N number of terms, but now the number of terms has gone down by 1. So capital N minus 1. So this thing is less than or equal to 1 plus capital N minus 1, which is equal to capital N. So you have now got this other inequality, that this is less than or equal to capital N. Now this inequality will get us what we want. So by part A, we again write this inequality slightly differently. We write capital N first, so that is greater than or equal to this thing. Okay, and In place of 1 we write this other sum, and that's where we have used part A. This sum is just like this sum, the only difference is that here we have the extra part, whereas here we have the greatest integer value of capital N divided by small n. And now this thing equals this. I have skipped some steps which are obvious. First you take the sum of these two sums, the corresponding terms get added. In those corresponding terms you have the common mu of n, which you take outside, and then along with that you have, multiplied with that greatest integer value plus fractional value of capital N divided by small n, which equals just capital N over small n. And then note that this capital N is independent of the index of summation. As the small n changes, capital N does not change. So you can push the capital N outside the sum first and then outside the absolute value function as well. Because it's positive, it just simply easily comes out. Now you see what you have got. Capital N is greater than or equal to capital N times this. Now you cancel capital N from both sides of this inequality. That first of all you can do that because capital N is non-zero, and the second thing is that the inequality will maintain its direction because capital N is positive, and that's how you get this. This is what you wanted to prove, right? Written slightly differently. So that's where the solution ends.